Okay, so not going to keep you very long tonight. Just going to show you a quick little bit about how to convert from rectangular to polar. And then you'll have practice up on that. And we've only got a couple classes left, and we don't have a whole lot that we need to do in chapter 10. There's just a couple of things I'm going to show you. And those of you going on to Calc 3 will need things like we're doing tonight. It'll be slightly different in Calc 3, but it'll be the whole idea. So I did send out a slideshow the other night, a PowerPoint slideshow. And in that slideshow was sort of the foundation of polar and rectangular coordinates. And then I showed some complicated looking graphs and showed the equations both in polar and rectangular. So one of the things polar is very useful is complicated relationships often are easier to work with. So we have to be able to convert. So we have rectangular. And we have a point over here. Let's say we have an X and here's a Y. So we have the X value down here, and we have the Y value down here. And that's why it's called rectangular. So every spot on this whiteboard has a unique address from the origin right here, which is the point 0, 0. So that's pretty basic. But we can also represent in a different way. Now we're going to keep the XY grid, but we're going to redo how we define what these points are. So over here, I'm going to put the same location. So this point from here to here is the same location, but instead of using XY, we're going to have this point here called the pole, like North Pole or South Pole. And then we can define the location as how far that dot is from the origin or the pole. And we're going to use the letter R here for radius. And then we also have an angle. So instead of the x-axis, we're going to think of the x-axis as the 0 degree direction, or we're going to think of it as the 0 radian direction. So both of those are the same. So same point, same distance from the origin here, but now we have a different way to describe it. And the word R, radius here, is because if you can imagine this swing, think of R as like a radar beam. Think of this as the airport, and this is an airplane, and the radar beam just goes around. And when the radar beam hits the airplane, it tells the person looking at the radar how far away that airplane is and what angle it is with, let's say, the east direction or something. So what we're going to do is go back and forth here. Now, I'm doing everything in the first quadrant because it just keeps everything positive. We could be doing this in any of the 4 quadrants here. So here's a right triangle. So this is the point XY. But we can also, so that means this, the height of this side of this right triangle is Y. And the length here would be whatever that X value is. And here we have beta. Okay, now pulling off what we know from trigonometry here. Oh, and this would be R. So we know that the cosine of that angle, the cosine of an angle is adjacent over hypotenuse. That's going to be X over R. The sine of this angle is opposite over hypotenuse, so Y over R. But what we're going to do, I'm going to multiply the R's to the other side. So I'm going to flip these over. And now we have a connection. Whoops, no, it's coming in here. Just click this person in. Hold on a second. So now we see we can think of these two equations as little translation machines. So we can go, if we know the x values and the y value, we can figure these out. And so that we also know that the tangent of theta is equal to y over x. So this gives us a means to convert back and forth. And there's one other thing that we can figure out here. Because of the rectangular coordinate system and we have a right triangle, we also know what r is equal to. And so r is equal to the square root of x squared plus y squared. So these 1, 2, 3, 4 equivalences give us a way to rewrite this point from xy. We can also write this as r comma theta. So there's two ways to name that point. We have the ordered pair here, xy, and we have an ordered pair here, r theta. They're both talking about the same point, just in different terminology. So that's underlying it all. And you have any questions about the basics yet? And there's more pictures in that PowerPoint. Anybody have any questions so far? So I'm just going to do a few examples of going from converting a rectangular coordinate to a polar coordinate and a polar coordinate to a rectangular coordinate. Just very basic stuff. Will be done pretty soon tonight. That'll be your homework over the weekend. It's not going to be a lot because I know you're getting all busy with papers and projects and stuff in your other classes. And then next week, we're going to do some calculus with all of this stuff. And that's going to bring us to the end of the semester. Okay, so let's convert. Okay, so there's a point in rectangular coordinates. So we have the point 4, 3, and we're going to rewrite that as r. All right, so we can start out. There's a number of ways to start out. So we're going to write it this way. I'll use a different color. That one's not showing up. Hang on a minute. So I know a lot of you have seen this in pre-calc, usually first or second pre-calc. So some of you have seen this and remember it. Some of you have seen this and you kind of think you remember it. And there may be some of you who've never seen this at all, but it's not such a big deal here. So we know what the x value is, so we can figure out r. So the r value here, the length of this red line, r is equal to the square root of 4 squared plus 3 squared, and that's the square root of 25, and that's 5. So I know the length of this. So if I go back to my silly airport example, if this is the airport and the r is the radar beam, that airplane is 5 miles from the airport. So we have a 5 right here. Now we need to figure out what the angle is, but that's not such a big deal. So now we'll go back and find the angle. And now we have a couple of ways to do the angle because we have r. We can use pretty much all of these, although often it's easier to use tangent. So the tangent of this angle, so the tangent of the angle is y over x. And so that means theta is equal to, now, you're going to need calculators for this, and you have to pay attention to whether your calculator is in radian or degree mode. Radian and degree, they're both the correct answer often, but it may not be right for that problem. So if the tangent of this angle is 3/4, then what's our angle? I'm thinking somebody out there's got a little calculator, they can pop that in there. I don't happen to have one in front of me, so what's that angle if the tangent is 3/4? So to do that, so you're just going to do, so theta is equal to the inverse tangent. There's another way to do it on your calculator. 3/4 is 0.75. So if somebody want to pop that onto their calculator for me and tell me what that is?
In radians, 0.6435.
So I'm just going to say, for purposes here, so it's about 0.64 radians. Thanks, John.
No problem.
And all you have to do is hit the button on your calculator to see what it is in degrees. And in degrees, that's, I don't know, about 63 or 4 degrees or something like that. Turns out to be almost the same in this case. 1 radian, not 60, it's going to be, let's see, 1 radian is 58, 60. No, it's going to be more like 50 degrees. 1 radian is about 58 degrees, somewhere around there. So now we know this. So we have 0.64. And we have converted that rectangular coordinate to a polar coordinate. They both describe the same spot. So it's just a matter of using these over here. So now let's go the other way. Let's start with radians. So let's say we are, I don't know, 3, pi over 4. And let's see what that is in rectangular. Fausto's coming in, hang on. Okay, so this is pretty straightforward. In order to figure out the x value, we just put r and cosine here. So our x is going to equal 3 times cosine of pi over 4. So x is going to equal 3 times 1 over the square root of 2. And so our x value is 3 over the square root of 2. Done. This isn't very difficult stuff, but if you've never seen this before, well, it's nice to see that. To figure out the y value, we do the same thing. So y will be equal to r times the sine of that angle. So that's going to be 3 times the sine of pi over 4. So y is equal to 3. So pi over 4 is 45 degrees. That's where the sine and the cosine are the same thing. So 1 over square root of 2. So the y value is 3 over the square root of 2. There, converted. It's not difficult, just takes a little bit of practice. So I'm just going to go through a couple of other things tonight. You have the weekend to get used to it, and then on Tuesday we're going to do some calculus stuff, so get a little bit comfortable with all of this. So questions about anything yet? All right. So now, let me show you something else. Looking at graphs and functions. So what does that expression look like? What does that look like?
Pythagorean theorem.
I'm sorry, Michaela, what?
Pythagorean theorem.
Oh, your voice is muffled.
Pythagorean theorem.
Oh, sure. But as a graph, if you were to graph this, what would it look like?
Oh, a circle.
Circle.
Yeah, Pythagorean theorem has to do with circles, right? So it looks like a circle. Can you be a little more specific?
Center 0, 0, and radius 3.
Nice. This is a circle centered at the origin and the radius is 3. X squared plus y squared equals r squared. Great. So that looks like this. So up here, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and looks kind of like that. We'll just pretend, all right? So that's a rectangular equation. So it's not a function, it's a relationship. One of the nice things about polar is they tend to be easier when your graphs are going round and round. The polar equation for this is that. That's the entire, these two expressions, this black one and this red one, both describe the same object. How's that for being really nice? Instead of x squared plus y squared equals 9, the equation for this circle is just r equals 3, which comes right from over here, by the way. Now, if I change this plus sign, if I now make that minus, now what does it look like? Anybody happen to know? It's not x squared plus y squared, now it's x squared minus y squared. Well, you can always put it into your calculators here. But if I want to convert that to polar, I can do this the long way. So x squared becomes this. So we get r squared times cosine squared theta minus y is r sine theta. So y squared becomes r squared sine squared theta. And we know that this is r squared. So I've converted from rectangular to polar, and something cancels out here. So all the r's cancel out, and we get cosine squared minus sine squared is equal to 1. And what that kind of gives us is something called a hyperbolic or a hyperbola. So converting from polar to rectangular and rectangular to polar back and forth, even if it's an equation, just involves using these, I'm going to call these identities or translation identities. We're translating from x's and y's into r's and thetas. So your homework's just some practice with this. There's not very many of them. And here's where we're going to be going with this next week when we start to do calculus on all of this. We're going to have functions next week where r is a function of theta. Okay. So when we see this notation, this tells us that we have a function. And so on a graph, the simple thing is it does not fail the vertical line test. So this says x is the independent variable and y is the dependent variable. So give me an x, you plug it into the equation, and out comes a y. So we're going to have r is a function of theta. So for example, here's an example of an equation in theta. We can have 2 times the sine of, hang on a minute, 7 zeros, nope. 2 times the cosine of 3 theta. If you're using TI-84s or probably anything else, you can type these equations in and it will graph those flowery swirls that you saw in the PowerPoint I sent out. So you push the graph button, you go to the math menu, and where it says FUNC, you just do POL. And then when you hit the graph button, you won't get Y equal, it will give you R equal. So this particular graph, let's plot some points here. All right, if theta is equal to 0, If theta is equal to 0, what is r? Theta is equal to 0, what is r? So you plug 0 in here, and what do we get?
2.
Yep, would be 2. Put 0 in here. Cosine of 0 is 1. 1 times 2 is 2. If theta is equal to pi over 3, what is r? So now you put pi over, do I want that? Nope. Wait a minute. Yeah. So you put pi over 3 in there, and what does r come out to be?
-2.
Nice, -2. All right. And if, let's see here, if theta is equal to pi over 6, so now you put pi over 6 in here, so r of pi over 6 is, this is sort of unit circle memory right here.
0.
0, nice, Michaela. There we go. So there's 3 pairs of points on the graph, and we could convert these to x and y coordinates. So it's just like an f of x, and this would be the x and this would be the y, and you put it down here. So I'm going to show you what this graph looks like. This graph looks like this. So when theta is 0, so this graph, it's not going to be a very good drawing, by the way. This graph looks like well, something sort of like that anyhow. So here, when the angle is 0, so right out here is the polar coordinate 0, 2. When the angle is, I might have drawn that wrong. Well, I might have drawn that picture wrong, but that's okay. So what we're going to do when we come back next time is learn how to do this. At this point on this graph, we have a tangent line, and we're going to come up with what's the slope of that tangent line. And to do the slope of a tangent line requires what? How do we find the slope?
Derivative?
Yeah, a derivative gives us the slope of the tangent line. But the tangent line, the equation of the tangent line is y equals mx plus b, because we're still on the rectangular coordinate system. So we have to come up with the equation of the tangent line, and that requires some converting from polar to rectangular and back and forth. Not a big deal. There's a formula for doing derivatives. So we're going to have that x, when we do this, our x is actually going to be a function of, when we convert, x is going to be a function of r, because we saw from before, we saw from just a little while ago. So this is what's coming up next week. Since x is equal to r cosine theta, this equation means that x is a function of r, but r is a function of theta. So x is a function of r, and r is a function of theta. So there's a composite function going up there. So when we do the derivative of this, we can't just do the derivative of this. There's a way we're going to use chain rule and come up with a formula for the derivative of every polar function. It's the same formula for every single polar function. And then that's where we're headed on Tuesday. So your homework between now and then, like I said, not a lot. It's just practice going from rectangular to polar, polar to rectangular, so you get comfortable with these equivalencies, and then a little bit of polar and rectangular equations. And that's all you're going to have to do for the weekend. And then we'll have Tuesday and Thursday to finish up, because besides tangent lines, there's also a way by integration to figure out the area inside the swirls of the polar functions on there. So Tuesday and Thursday, we're going to do derivatives and integrals, and that's going to wrap up the semester for us. So, anybody got any questions yet? Sounds like a lot, but it's not going to be. The nice thing about tangent lines and polar is it's the same formula all the time. Doesn't even matter what the function is, same formula. So anybody got any questions? A short, like I said, it's a short night tonight. 'Cause I know you got,
Question. Oh, sorry.
yeah, go ahead.
Like, can like R of theta be written as like R equals F of theta or no?
Oh, sure. So that's just a generic thing. So if R is a function of theta, then R can equal, right, F of
Okay.
theta. Yeah,
Just making sure. Thank you.
and that's the specific function. So this is just generic function notation, right?
Yeah.
So we can say that Y is equal to F of X. Although usually, instead of using Y, we use this notation, right?
Mm-hmm.
And instead of using R when we do the derivative, we're going to use this notation. And we're going to have the derivative of F of theta, and that's going to be our function. But because the X also works its way into there, there's just a couple little subtleties I've got to show you.
Thank you.
Yeah, no, it was a great question, Michaela. So that's where we're headed. So we are in, by the way, tonight. Your homework is coming from section 10.4. I'm only going to give you the first few homeworks on there, but you should look through 10.4. It shows you how things get graphed, and so it'll get your head into the game of polar coordinates. And they do look kind of nice. They all look like, I don't know how many of you had that toy. How many of you, when you were little, or even maybe now when you're big, have or had a spirograph? Anybody know what a spirograph is? It's a toy. So it's these plastic rings that you put on paper, and they like have like gear wheels on them, and you put a pencil in one, and you roll it around the inside, and that brings out all these swirly looking things. Anybody? Oh, Kyle, yeah, you had one, right? Yeah, they're kind of cool. So you were doing those, that's what polar equations look like. Oh, well, Nicholas, you should check out Spirograph when we're off class. They're pretty cool. It comes in a little box. It's plastic things, and there's wheels. There's wheels within wheels, and you put your pen in there, and it draws out these really kind of cool looking shapes on there. In fact, if you got any little kids in your family, not a bad present, by the way. So you might want to check that out. Okay, that's all I had for tonight, folks. Yeah, at least you didn't have to spend time driving here, right? So I'll get, and I'm going to start the grading on the tests tomorrow. The tests I got in last night. Today, on Tuesdays and Thursdays, I go from like 11 or 12 in the day up until this class, so I didn't have time to do any of it yet. So I'm going to start the grading on those tomorrow. Okay, I'm good if you're good. And Kate, I'll check that email right after I sign off here. Okay, good night, everybody.
Thank you.